Alright, so in this video I'm gonna be explaining another important article with the title Graph Neural Network Pooling by Edgecott. This paper in ICLR 2021. Of course, it is inspired by this article in 2019 So graph neural networks are very efficient at solving tasks in graphs such as node classification or graph classification. They come from adaptation of convolutional neural networks and images to graph structured data. These models are very effective at finding patterns in images that can discriminate images from each other. Another aspect leading to their success is their ability to uncover hierarchical structures. This comes from the pooling operation that produces different versions of the input image at different scales. The same way, we want to identify patterns at different scales in graphs in order to improve the classification accuracy. So compared to the case of images, it is not trivial to develop a pooling layer on graphs. This is mainly due to the fact that in graphs, nodes are not ordered and have irregular neighborhoods. But when it says not ordered, I can say many papers such as, let's say, Geom GNN, that it produces some kind of local structure around each node of the graph. So they use virtual nodes to connect the neighborhoods, and then they project here. Then they have higher order aggregation, high order, and then low level aggregation, which connects different virtual nodes to each other. And there are many different ways to create an order. But the idea of this paper is just pooling. Just a pooling layer based on edge cuts in graphs. This pooling layer works by computing edge scores that correspond to importance of edges in the process of information propagation in the GNN. Moreover, we define a regularization function that aims at producing edge scores that minimize the mean cut problem. The objective is mean cut. For example, there are different objectives such as modularity. Also, mean cut is not new. Some people also use max cut. They see it differently. They say, okay, we can downsample things that are very similar. So they increase the number of edges between clusters and say, okay, we pick one of them. So they are coarsening. You see, there are many ways to create hierarchical graph pooling. But the contributions of this paper are these four. And most coarsening strategies are based on nodes, either by finding clusters, but this paper is just about graph cut. We focus on edges to uncover communications of topologically close nodes. So they classified different kinds of papers on this pooling. For example, top K cluster identification is good, but has high computational complexity. Edge-based pooling is very simple, but you know what? Some people criticize this and say, they don't fix the amount of clusters. For example, we have K clusters. They don't fix it in advance, but the graph shows, the distribution of the graph shows that how many it will appear. We only say how many layers we are going, 14 layers, for example. And then we have deterministic, which is not really interesting. So the main similarity with our work is we compute edge scores to like this graph attention mechanism. So you know how graph neural networks work by this message passing. So we have aggregation and update. For example, we have many types of graph neural network, GCN, graph isomorphism network, graph attention network, and many other. So we need to find a scoring mechanism. This is scoring mechanism. So what is this S sub ij? First they define like this, then they notice that what if we want to be agnostic to the direction of that. So because a non-directed is both of them, so we try to make it symmetric. So we are symmetrizing it and making it symmetric. So by applying sigmoid function to attention, we compute importance of edge. So Sij, if it is high, it means that this edge is essential. Maybe it's a bottleneck. It should be in the graph. If you remove it, it becomes a very disconnected graph. So after creating the threshold and then normalizing, this is what you really need. Because once you get this, you can update your features. Also your adjacency. You can update it using this. And notice that this one is created by the result. It's just a result. You just put the numbers inside that after you do merging. So we do merging, and then this paper, by the way, is rejected in ICLR, but it is very valuable. This is very interesting. I know why they rejected in ICLR, but this paper is very valuable. So they represent Z as different representations. And you see here, it's very similar to some other papers as well. For example, min cut idea is not new, though they use min cut. But the way they do is much easier. An approximation of the ratio cut problem is this. And then they said we can have, of course, I've explained many papers of Bianchi that he used min cut, and he created very successful models, very good models on the basis of min cut objective, not on the basis of, for example, modularity or any other objective. Because it's min cut is very natural for clustering. You see, we have to have very few edges between clusters. And then they did experiments on these, very popular. These are for graph classifications. This is Colab, Cora. There are many data sets. Of course, Colab and Cora, these are very simple because they have high homophily, less heterophily. So they are very simple. That's why state of the art is more than 80%. And they tested on these. So you see the training, validation, and testing. Statistics node classification. For Cora, CiteSeer, and PubMed. These are, I can say most of them, all of these three have very high homophily ratio. That's why each node, the neighbors have very similar labels. And you see the different models. EdgeCut is the proposal, and you see that it is improved. It has improved debug, but it is less than graph attention. Graph attention is very complex, but the drawback of graph attention is the computation complexity is high. Otherwise, it's very accurate. So sometimes there is trade-off between accuracy, time complexity, cost. So this triangle always you always see that. Graph UNet, they use UNet for image segmentation, but then some genius person generalized it to graph. So Now this is the architecture of graph unit that we downsampled, and then the upsample and then reconstruction error. And then that's it.